Good morning, good afternoon, or good evening, ladies and gentlemen, depending on where you are on the planet right now. A very heartily welcome from my side. My name is Bippes. I'm a product manager for the DriveAFM at NanoSurf. And today I would like to introduce you to the DriveAFM. It's been launched almost 3 months ago, in December 2020. And since then we've received positive feedback from the community, a lot of interest in the product, and today I want to give an introduction into the system, show some of its features, and also mention why those features are important for certain applications or for certain kinds of measurements. So the DriveAFM is our new flagship AFM. It has a number of features that we put into. I will mention them in a second. And we invested quite a bit of effort, resources into the development of this nice tool. So what is now in there in the system? So what does it make so nice? The DriveAFM features a clean drive. It's a photothermal excitation of the cantilever, which allows you to, especially in liquid, operate the AFM very nicely. Also, it's fully motorized, which is a huge benefit for the ease of use of such a system, but also opens up possibilities for automation of the system. It has the capability of using small cantilevers. Small cantilevers bring some advantages during operation, and I will talk about that a little later. We have a new scanner for completely new development with a high resonance frequency, a direct drive actuation, and a large range, which is still capable of doing very high resolution imaging. Along with the scanner, to make use of that scanner, we also developed new control electronics, which is very fast, has a low noise, but at the same time is also equipped with a very high resolution control possibilities. We have a bunch of accessories. I will briefly talk about them. I will not show most of them, but just to know there is a full set of accessories already available with the DriveAFM. It's constantly expanding. And last but not least, I would like to use this presentation, this webinar, to show you images and what we can do with the DriveAFM, what we achieved so far, and how these technologies that we built into the DriveAFM help you to obtain these kind of images. As mentioned, the DriveAFM is a system. It's not just a scan head, but of course the scan head is an important part, a very important part, which has an all-new scanner design and the photothermal excitation included. But also, as said, there is the control unit and the high voltage amplifier that is needed to drive the direct drive piezos and the scanner. And I will talk later a little bit about this. And as said, there's also a bunch of new accessories. So overall, the system was designed keeping in mind that it should serve the needs that you have today, but it should also be safe for the future. So it should in a few years still be able to do state-of-the-art research with this kind of system. And I think with the technology we put inside the instrument, this is really possible. The DriveAFM comes in different flavors, so it can be used as a tabletop system. It's often mainly for material science application or physics. There it's mounted on an anti-vibration table and has a relatively small footprint. At the same time, it was designed to also be able to be mounted on an inverted optical microscope. And there we support the major suppliers or brands of optical microscope, Zeiss, Nikon, Leica, and Olympus. And we have stages that allow you to mount the AFM on top of those microscopes. So let me start with some images from the kind of biology realm of AFM experiments, since my background is also from this area of biology initially, I like these very much, but they are also quite illustrative to what we're going to talk about. So the first image, also one of the first images that we took with the DriveAFM on a real interesting sample, is a high-resolution image on Bacteriorhodopsin, a purple membrane, which is a molecular assembly, a 2D crystal, forms a 2D crystal in the membrane of some halobacteria. And you can see there's this lattice, and encircled you see this trimer, which is also encircled in this correlation average here, which is made of 3 proteins. And so this is a very well studied sample in the world of AFM or bio-AFM, and so it's very well known how this should look like, and it should basically look like this. And now if we take an FFT of this image, we get kind of a diffraction pattern, which tells us the resolution of this image. And what you see is you have these 2 circuits at 1 and 0.75 nanometers, and there is some spots that are outside of this 0.75 nanometer ring, so which means that the resolution is actually higher than that, and this is a really good resolution on this kind of sample. And I want to remind you, this was taken with a 100 by 100 micrometer XY range scanner. So I was very happy, since this was also one of the first images that we took with the DriveAFM. This is a bit more demanding. So this is a double-stranded DNA, and resolving the secondary structure of the DNA is typically a bit a challenge. And what you can see here, and we were pretty happy about such an image, that you can see these banding, these stripe pattern here along all of those strands. You can see this ripple banding, which indicates that this could be a secondary structure element, or the secondary helix of the DNA. Now, if we zoom in, we can take a cross section here across a piece of the DNA, and if we then look at it, we see there is these hills or peaks and these valleys, and measuring the distance between or every second of these, we come up with an average distance of 3.4 nanometers, which indeed corresponds to the pitch of a double helix in the bDNA structure, which is very well established by crystallography. So we are pretty confident and pretty sure, also looking into literature, that what we see is indeed secondary structure of DNA. And this is, as I said, it's not the easiest measurement to do. So, but in the end, what does it need then to have an instrument that is capable of doing that, and ideally doing it regularly and very easily? So the DriveAFM, as I said before, we implemented a number of technologies, and the interplay of those technologies is very important. Each on its own is interesting, but it's the interplay and having them together that makes the AFM performing great. And I would like to introduce some of these key technologies now, and later on, when I show you more data, more results, you will always see these small icons that you can see here on the screen, indicating some of these technologies along with the images. So one thing that we took care of is that the system has a low system noise flow, so it has a low noise performance. This is important because if you have a high noise in your system, you're not able to detect small changes and do gentle imaging. So particularly what we can do is we can reach noise flow of the system which is well below 15 femtometer per square root hertz, which is excellent. And so we get there by using a low noise and low coherence light source, but also low noise in the high bandwidth detection. So also at high frequencies we still get low noise values. What you see here on the right hand side, actually this is the resonance peak of a small cantilever in liquid, So that's why you have the peak here. But important is the low noise at the beginning before we have the resonance effects coming in. So then, on top of this low noise light source and low noise detector, we also have to make sure that the signals that we get out of the scanhead, that they process them, and we process them, that they are also low in noise. And we created the CX controller, which you see up here. And actually, this is one of the lowest noise, or it's the lowest noise controller currently that we know of. We have noise floors at 1 Hertz frequency of 25 nanovolts per square root Hertz, which is excellent. And if we are going to higher frequencies, it's even below 50 nanovolts per square root Hertz. So it means we have an excellent and low noise controller to read our signals, but also to drive our instrument. On top of that, we made sure that the system or the controller and the feedback loop has a very low latency in the digital and in the analog part of the system. This is very important to have proper scanning, to have a fast responding feedback for fast scanning, but also for demanding samples, as we will see later on. And as I said, we have a low noise controller. What is also important is that it has a high resolution. So that means that signals that we send out to the scanhead have to get there at a very high resolution. So you have to be able to precisely control the scanner especially. The scanner is also a new development. It's a direct drive scanner. It's a compact scanner. It has a very stiff design. Yet it has a 100 by 100 by 20 micrometer X, Y, and Z range. And we get there by using a technique which is called direct drive. That means we do not amplify the motion of the piezo elements that we use to actuate the scanner. We just use the pure actuate or extension of the piezo. And this way we can build a stiffer and more robust scanner. Also, it's much smaller. As you can see here, this is the whole scanner unit. And down here in these holes, you can see indications of the piezo-stacks elements. With the scanner being stiff, it also has a high resonance frequency, which is important for fast scanning at some point, but also it reduces the acoustic sensitivity of the scanner, so it's less disturbed by acoustics. And you can see over here that we have a hole in the top of the scanner, which is important to provide optical access, which we'll need especially for bio applications. And you see here there's a lot of stuff which is sticking around the scanner, around the actual scanner. And this is also part of why we can build a stiff and a compact scanner. It's the 2D optical guiding tip scanner architecture. And basically we have a guiding system here on the scanner, which allows us to have the lasers or the light sources off the scanner. So the light sources are not sitting on the scanner, not scanned along with the scanner. It's just a few passive low mass components that are actually moved along with the scanner during the scanning process. And this way we can have multiple light sources and we can have everything fully motorized. And yeah, having these multiple light sources enables the clean drive excitation. So what is actually clean drive excitation? Clean drive excitation is a very stable way of exciting the cantilever. So what you see here is we're driving the cantilever at an amplitude of 3.5 nanometers, and the cantilever is immersed in a little drop of liquid. And as we let the drop of liquid evaporate down here, what happens is that the amplitude doesn't change a lot. It only changes here once the droplet is basically evaporated and the cantilever is not immersed in liquid anymore. And this is over the course of almost 3 hours. In liquid, typically the cantilever, with the typical excitation that we use in liquid, or that we used before, the piezo excitation, this curve would change a lot. The reason is that the environment changes by changing the volume of this droplet, And with the piezoacoustic excitation, this may be a problem. So, but how now does it work? How does the clean drive work? So as I said, so far one was using a shaker piezo to excite the cantilever and make it oscillate. And the oscillation is read out by the readout light source, and which is focused on the back of the cantilever and then reflected on the photodetector. With clean drive, what we do is we use a second light source that we focus to the base of the cantilever, and we modulate this light source in intensity. Actually, we're using a 785 nanometer NIR laser source, which allows us to also be compatible with optical microscopy and biological samples. And by modulating the intensity here, we locally heat the cantilever at its basis, and this way we start exciting the cantilever. But we just excite the cantilever, not the whole chip and not the whole scanner or the whole cantilever holder. It's just the cantilever itself which is excited. And this way the coupling to the environment is much less. And yeah, what you see if you do piezo excitation, you typically get such a resonance response in liquid. If you do that now with a clean drive, you get a very textbook-like response. You have one single resonance peak that you see. And this allows you to reliably, also unambiguously tune where you want to drive or you want to excite your cantilever, at which frequency, at which amplitude. This forest of peaks will change every now and then during operation in liquid when using the piezoacoustic excitation. And it will also change when you change the distance to the surface, things like that. So it's rather unstable. Okay, so we have now this clean drive. We have two light sources, and both of these light sources have a small laser spot that allow us to focus them on these small cantilevers. So this cantilever is 10 micrometers wide, 20 micrometers long, and the laser spot that we have is optimized to fit on such cantilevers. These cantilevers have a number of advantages. They have high resonance frequencies, they have higher bandwidth compared to regular cantilevers. Since they're shorter, they have a higher sensitivity, and at the same bandwidth, operational bandwidth, they have typically a lower noise. Yeah, and all of these features together, combined in the DriveAFM, allow us to basically take such nice images where you can see the basically the secondary structure of DNA, for example, and which make the user experience so much better and also take the performance to a next level. So in the next few slides, I would like to show you some more examples. So let's start with some bacteriodopsin. So this slide, I would like to show that you can go from molecular lattice. So you can think of a bacteriodopsin, a protein, being a molecule which forms these trimers. So we have a molecular lattice here that we can clearly resolve, and yeah, we can also resolve the atomic lattice of mica with the same scanning unit, and also HOPG. So that's not a problem to resolve these atomic lattices. And up here in the upper left corner of the slides, you will find some of the features which are important in order to get these resolutions or these images done. In this case, it's important that we have a scanner which can scan at a high resolution. It's important that we have the low noise performance, especially on these muscovite mica and HOPG structures. The topographic changes and the signal that we get out are very small, so we have to have a low noise system, otherwise we would not be able to detect topographic changes in these surfaces. Also, the controller has to be precise enough to address the scanner to scan at these small scan ranges with such a big overall scan range that's possible. And again, the motorization here is also an important feature because, for example, bacteriodopsin or any system, if you have a kind of equilibrated environment, you don't want to break it because, especially in liquid here, your cantilever drifts a bit. Now you can just adjust everything through the software without opening the enclosure, without touching the instrument and breaking your equilibrium. Yeah, but you can not only image, of course, the crystal lattice or the lattice of a structure. We can also measure step heights. That's a slightly larger structure, so we can measure step height of crystals. For example, here we have silicon carbide, which forms these terraces, and you can nicely see there is the staircase-like pattern when you do a cross-section along this image. And if you also do a height histogram, that's what you see here in gray, you see basically the counts of pixels at a certain height as a function of the height. This also indicates there's a clear 1.5 nanometer spacing between these large terraces. And in the image you can sometimes see here some smaller areas which have an in-between height of 0.75 nanometers between each terrace. We can also image, of course, steps in HOPG, so that is graphite, steps in graphite. And here you can see from A to B and from C to D we have step heights of 330 picometers each, while A and C have a larger separation as well as B and D, because there's a layer of, or multiple layers of graphite on top of that. And now we have small structures, but we can also use the same scanner to image very large structures, whole cells. I mean, here we make use of almost the whole scanning range. This is an 80 by 80 micrometer image, which we see multiple cells sitting in. And we can do that with exactly the same scanner as we can do with the high resolution images. And in this case, it's important to have this large range. Also, the 20 micrometer Z range are beneficial for working with cells, as they can be pretty high, especially in the area where the nucleus is located. And also the clean drive excitation here is a big plus, since you can stably image over a long period of time. I said that the scanner allows for optical access, and this is important that we can illuminate with the optical microscope through the scan head and observe the sample to position, for example, the cantilever over a sample of interest, and just observe what's happening while we are scanning, for example, but also to identify targets that we want to investigate. So now we looked at different sizes of samples, but also there is a need for stability of scanning. I said with the clean drive we have a very nice stability in the excitation, and so this is one important factor, but also drift is another important factor. What you will see now is two images taken at the beginning and at the end of 300 consecutive unattended scans on the silicon carbide sample, and this took about 14 hours. And as you can see, these images are basically identical. So that means you can identify there's some small defect over here, which is also here. So there's almost no drift in these measurements, and also the step height is unchanged. We have more or less the same height distribution compared to the first scan when we look at the 300th scan. And another indicator is that we can measure the roughness, for example, on this terrace here or on this terrace, and they are basically identical. So it means we have hardly any tip wear, which is also important for stable scanning, so that you do not blunten your tip, so that you can image gently but reliably over a long period of time. Fast and stable operation are also very important for AFM, especially if you want to image a lot of samples. Fast operation is a benefit. What you see here is an image of a copolymer imaged in phase contrast. You see a phase signal up here and a topography signal down here, and a line rate of 20 Hz with the DriveAFM. So this image was taken in air, and so here comes the small cantilevers come into play, because they have a higher bandwidth, and just using regular cantilevers at a few hertz of line rate, their response would be too slow to actually properly track the surface and give you a proper topography. As I said, the controller was designed to have a low feedback latency, and also the scanner is set it's stiff, so it has a high resonance frequency. That means it can respond fast. It can respond faster than comparable scanners out there on the market, as it's a direct drive and stiff architecture. And this is important, for example, looking at such grating samples. They are often used in industry for different purposes. You have such gratings, and they're quite demanding. So you have very deep trenches with steep walls, and if your feedback is too slow and cannot follow these structures nicely because your piezo is too slow or your feedback itself is too slow, you would just ruin your tip. And over the course of a few lines, you may see that your tip just degrades, and you cannot follow those nice trenches anymore. I showed a lot of imaging applications by now, but there's also other things that we can of course do, and one of them is force mapping, force spectroscopy using the AFM. And this is often used to investigate mechanical parameters like the Young's modulus, adhesion, or stiffness. And the example that you see up here is a force map taken on live cells at 37 degrees in cell culture medium. And you can see here the elastic modulus plotted on top of the cells. And you can see here the histogram of the elastic modulus distribution on those cells. And this white part here corresponds basically to the glass surrounding of the cell of the petri dish. Another example is, for example, a polymer blend. This is now a measurement that's done in air. It's more material science application. We have relatively high elastic moduli, up to a gigapascal here, while, for example, for the cells, they were in the 10 kilopascal range. You can also obtain a map. You see the distribution of different polymers basically within this blend. So I told you there's a number of accessories. I just basically want to show that chart for the accessories. It's just to make sure that you know that we have everything that's needed to be on an inverted optical microscope, so we can heat also our samples to physiological temperatures. We can work in petri dishes. We have accessories to do force spectroscopy also with whole cells, so we can separate wide enough. We have FluidFM, which is a technology that allows you to use hollow cantilevers to do different kinds of sample manipulation. For the material science, we have a variety of, for example, heating and cooling stages. We have a heating stage. There's a number of electrical modes. Some of them I will just quickly present later on. There's an electrochemical stage. There's a lot of things that allow you to do a huge variety of experiments with the DriveAFM. And some of them, some of the electrical modes I would like to go in now. One of them is the Caravan probe force microscopy, which gives you some information about the contact potential difference of your materials. So what you see here on the left-hand side is the topography image of this naphthyl end-capped oligothiophenene, which is basically adsorbed on graphene. And you can see there's different islands of different height. There's these rod-like structures. And with the Caravan probe force microscopy, we can see that there is contact potential difference between, for example, this island here and that island over there, which can give you some idea on the arrangement of these oligothiophenene molecules in these islands. So KPFN, or Caravan probe force microscopy, can be done, of course, with the standard DriveAFM, with the CX controller and the DriveAFM. Again, the photothermal excitation is a good plus. because you can again reliably drive your cantilever, and also the low noise signals or low noise capabilities of the system are important, because we detect some oscillations or some induced signals on the cantilever as well with a second lock-in amplifier. But if you want to do more advanced KPFM, there is also the possibility to have an advanced KPFM package, which includes a Zurich Instruments lock-in amplifier, which provides more advanced modes, which provides also much more control, but also is, for example, key if you want to develop your own modes, your own KPFM applications, for example. And we will have a webinar, I think it's on April 29th, on KPFM. I can highly recommend this webinar to you. So feel free to register and check our website and our postings for this webinar. Then we also have another electrical mode, is the piezo response force microscopy. What you see here is this 2D ferroelectric material adsorbed to silicon. And what you can see here nicely is the amplitude of the piezo response of this material, and also the phase change of these materials, depending on which material you're on. So it forms these islands, it has these structures. So it's basically a thin film on silicon. And yeah, we could get a quite nice contrast here. So this is almost 180 degrees phase change between the different phases or parts of this sample, which is what one would expect to some extent. Yeah, here you also see that we have a top view optics, which allows you to basically navigate also if you don't have an inverted optical microscope and you're working on opaque samples, to position your cantilever above the area of interest on your sample. I was mentioning it before a little that for application development and for new mode development, we have the possibility to interface, for example, with the Zurich lock-in amplifier. So the CX controller has a number of user inputs and outputs at different resolution and speed that allow you to interface with third-party electronics, third-party equipment. We are also currently developing with some key opinion leaders a breakout box, which basically allows you to have access to most of the control signals that go towards the scan head, and also the signals that come back from the scan head. In the end, this would allow you to do kind of a custom microscope control if you want to have special protocols to run your system. We also have a Python repository for custom scripting, which allows you to, if you have something that is very repetitive and you want to automate a certain process, you can do that with the Python scripting. But you can also build, if you're developing new applications, you can build your own graphical user interfaces, which would allow you, for example, to address the CX controller, the AFM, the scanning part, but also some other functionality that you may want to couple together with the AFM. Could be, for example, a lock-in amplifier or a variable magnetic field sample holder. So here there's also some more information on this scripting interface and the Python capabilities that you can look up if you're interested in that. And again, we will have a Python scripting webinar. The date is not yet fully fixed, so stay tuned and check our website for the webinar announcement. After coming from the electrical modes and programming and customization of electrical modes, we switch a little bit the topic now. We go to special probes. In this case, electrochemical probes. NanoSurf recently acquired Scuba Probe Technologies, which is a company located in the Bay Area, and that is specialized in probes for scanning electrochemical microscopy. That means it's producing probes, or it designed probes that are fully isolated, except for the very end of the tip, of the apex of the tip. So you form a small electrode at the end of the cantilever tip, which allows it to do electrochemistry in liquid solution and all kinds of other electrochemistry related experiments in solution. And since we acquired this company, we are now in the process of developing a turnkey SECM solution for the DriveAFM. Staying a bit with specialty probes, I mentioned FluidFM before. FluidFM is a technology which is based on hollow cantilevers, in which case you have a cantilever adapter to the cantilever, which is sitting here, and you have a connection to a pressure controller, and from there you can apply pressure through a channel which goes until the end of the cantilever, and which has a hollow apex or an opening at the end of the cantilever. And this way you can do quite a number of different things. So it's a multifunctional manipulation tool, and there's a variety of things that you can do with this kind of experiment. And for example, you could do single cell spectroscopy. You can aspire a cell from a substrate and lift it off. You can aspire colloids. You can inject material into cells, for example. You can measure the adhesion of single bacteria. You can isolate single cells. You can extract material from cells. You can do lithography, and you can do what we call spotting, so depositing small spots of material on the surface. And this is what I have a small video on. So what you see here is the cantilever periodically or subsequently touching the surface and forming an image of something. We'll see in a few seconds. And here we use these cantilevers as small pipettes, basically, to put small droplets on the surface. So the diameter of this circle is 60 micrometers, and the spots are relatively small. And in the end we have spotted a smiley. And for example, the position of these dots have been calculated through a script and transferred into the AFM software, which then use those positions to spot the liquid droplets on the surface. But you can of course do a lot of other things with that thing as outlined on the left hand side. And if you want to know more about FluidFM, visit our website. We have a section on FluidFM there. FluidFM, as I said, we can aspire cells, and I'd like to address now, as a last topic, measurements on the mass of cells. In this case, we also attach cells to the end of a cantilever. This could be a regular cantilever where we chemically attach the cells, but it could also be a FluidFM cantilever that we use to aspire a cell and fix it this way on the cantilever. And so what we do is we use the clean drive technology, so basically the photothermal excitation, to gently vibrate this cantilever and observe its resonance frequency and the change in the resonance frequency. And for that we need a very low noise system. So you see we just move here a few angstroms. That means we have to have a very good detection of the cantilever oscillation, and we also need to have a stable oscillation or drive of the cantilever. And this is only possible with the clean drive technology, because with the piezoacoustic excitation you would end up nowhere. The signal would be not clean enough. The phase response that we also monitor is just a mess with a piezoacoustic excitation. And so this technology is actually non-invasive, so you can measure the cell stays alive, the cell is happy. It's fully compatible with optical microscopy, so you can do transmitted light microscopy, fluorescence microscopy, to see how the cell changes over time, for example, if you do a time series. And the system, or this technology, has a very high resolution in terms of the mass measurement, so we can detect like 0.1% of mass change. So a cell weighs a few nanograms, and we can have picogram mask resolution here, and also very high time resolutions, around 10 milliseconds. And yeah, you may ask, what can you do with that? So there's different examples. One shown here is that you see there over the course of something like 40 seconds, the cell mass fluctuates, and there's fast fluctuations marked in red and more slow fluctuations marked in green. And by blocking, for example, water channels, aquaporins with mercury chloride, these slow fluctuations can be reduced. So one can attribute those slower fluctuations to water traffic through these aquaporins. And there's other things that you can, of course, look into. For example, what has been done, for example, in this very nice paper by David Martinez from the Daniel Müller group in Basel, to look at what happens upon virus infection. And yeah, so this is a very nice technique. And there's also something coming up, some announcements to take place in Q2 this year, probably towards end of May. Yeah, so I think I'm almost through. Let me summarize the DriveAFM again a bit. I hope I could show you that this AFM is great for doing work with high resolution samples which require high resolution imaging, but also for samples which don't require high resolution but a large range, or if you want to look at electrical modes, electrical properties of your samples, or mechanical properties of your samples using force spectroscopy. So again, to quickly summarize, the full motorization is a big benefit, especially if you work, for example, in biosamples where you have equilibrated temperature in an acoustic enclosure, for example, and the cantilevers tend to drift quickly. You don't have to break your environment. You can simply stay in the equilibrated environment. But also for anything where you want to do automated measurements, repeated measurements, long time measurements, it helps so much because you could adjust things during the measurement without opening the enclosure or even touching the instrument. The clean drive is mainly beneficial, of course, in liquid because we have this very clean excitation, but also it's a very stable excitation, which is also very important for measurements in air. Also, if you want to do measurements over a long time, this is the way to excite your cantilever. Saying that we have clean drive excitation, the DriveAFM is of course also capable of doing the regular piezoacoustic excitation. It's just that the clean drive works so much nicer and so much more stable. As I said, we have these small cantilevers, which are very important if you want to do imaging, fast imaging, and they also have a superior just performance in with the clean drive. The high resolution and high resonance direct drive scanner, that's something that is the heart basically of our AFM, of course. It has a high resonance frequency, so it allows us to scan fast, but also we can scan at a very high resolution because we have also these low noise and fast control electronics that can address the scanner precisely to allow smallest motions and small scan areas. I said that there's a number of accessories. I didn't go into details here. If you're interested in what accessories we have in detail, feel free to visit our website. With the DriveAFM, the accessories are also listed that are available for the DriveAFM. But it's a huge number of things that you can use to extend the DriveAFM. Yeah, and last but not least, I hope I could show you that we can reliably and successfully and nicely image a number of different parameters, topography on small ranges, on large ranges, electrical properties, and non-mechanical properties. So with that, I would like to say thank you for your attention. Hope to see you next time, or to welcome you again for one of the other webinars that are upcoming on KPFM, on the Python scripting, and also there will be some event for mass measurements taking place in Q2 this year. So with that, it's up to me to again say thank you and asking you for questions.